Today in class we looked at distance on the coordinate plane. It's very, very similar to the Pythagorean theorem. We just make the triangles within the coordinates. So again, our Pythagorean theorem states that as long as we have a right triangle, then their side lengths, the two legs, A and B, when squared, will equal the length of the hypotenuse squared. It also works in reverse, so if you are looking at a triangle and you're not 100% sure if it's a right triangle, you can plug the side lengths into this formula, and if it equals, you do have a right triangle. So what we're going to look at today is what happens when we're looking at distance on a coordinate plane. So say I've got my first point here, my second point here. Actually, let's start with this one instead. Okay, from here to here, point A to point B, I'm able to count the distance between these 2 points because they're following the grid. Ooh, I thought I had to sneeze. So from A to B, 1, 2, 3, 4 is that distance. We're able to count it. The same thing is true if our line is perfectly horizontal, say from B to C. That was 3. Where the Pythagorean theorem comes into play is when we're looking at these diagonal distances from like A to C. We're unable to find the exact distance by counting because we're not following the grid. That doesn't count as a full box. That doesn't count as a full box. That doesn't count as a full box. That isn't a full box. That's not a full box. So we're not 100% sure if we can actually say this to any degree of certainty. So what we end up doing is we take our points. Let's say our point is here, A, and our point here, let's move that one actually, let's put it here. B, I want to know how far away is A from B. What we're going to do is we're going to create a right triangle. We create a right triangle by drawing a line straight down from this tallest dot, a line straight across from the lowest dot until they meet and create a 90-degree angle. We have now made our right triangle. We could have also have made our right triangle on the other side of our line. It is the exact same triangle, just inverted related to the first one. Just like before, we're allowed to count when it's perfectly flat or perfectly vertical. So that's a distance of 3 right there. There's a distance of 1, 2, 3, 4, 5 right there. Our unknown length of our right triangle is our hypotenuse C. So we're going to take A squared plus B squared is equal to C squared. So A will be 3, B will be 5. These could be flip-flopped if we wanted to. I typically make the smallest number A, next smallest B. That leaves our largest number C, which is what it has to be. Our hypotenuse has to be the largest side. That gives us 9 plus 25. That's 34. We square root both sides. So I'm going to take 34 and I'm going to square root it. I get this crazy long decimal. We're going to round it to 1 decimal place, so we're going to look at the 3. Since it's a 3, so 4 or less, that keeps our answer 5. Oh geez, I was lagging there a little bit, I guess. 5.8 for C. And there's our distance from A to B. Let's try it again. Let's say our point is up here, and we've got this really, really narrow but really, really tall triangle. So from A to B. So we draw a line straight down, then straight across. We could have also just as easily drawn our triangle on this side. Both are the exact same. From B to this point right there is 2. From this dot to that dot, I'm going to count 1, 2, 3, 4, 5, 6, 7, 8, 9. We are once again looking for the hypotenuse. So 2 squared plus 9 squared equals c squared. So that's 4 plus 81. That's 85 when added together. We're going to square root, so we bring it back down to just the length of c. So we take 85, square root it. We get 9.21. So again, 1 decimal place, so the 1 keeps us at 9.2. It is also possible to set up these problems without having to graph a single point. I'm going to keep the graph here just so we can check. Let's say point A is listed at -2, 3, and point B is listed at 1, 6. We could easily come over to our graph. Here's that's -3, 3. -2, 3 is right here. 1, 6 is right there. We could easily count the squares. But instead what we can do is we can find our horizontal distance, our x distance here, and our y distance here, and set up our problem this way. So I'm going to look at my x coordinates only. How far away is -2 from 1? So that's measuring this length right here, just without having to graph it. From -2 to 1, that's a distance of 3. It's the same number of box we see over here. We then do the same thing with our y distance. From 3 to 6, it's also 3, but that's what we see from 3 to 6. Those are our 2 legs of our problem. So we add those together, we get 18 equals c squared. Divide both sides by, or square root both sides. 18 square rooted gives us 4.24. So again, the 4 rounds the 2 down and keeps it at 4.2. So we can do this without graphing a single dot. Be our last example we look at. Let's say I've got 5, 1, and I've got 1, -5. First, we're going to find the distance between the x's. Being negative or positive in this case does not matter. Distance doesn't have negatives. If you travel a distance, you have covered that distance. Only what negative and positive controls are the direction. So if you think about football, when someone gains 10 yards, it just means that they move the ball 10 yards forward. When they've lost 10 yards, they move the ball back 10 yards. In both cases, the ball moved 10 total yards. The negative positive controlled which way we actually move the ball on the field. So from 5 to 1, we might be like, that's -4. But overall, we still moved 4 boxes. From 1 to -5, we might think, oh, that's also 4. But we would jump from 1 into the negatives. This is actually a -6. And again, negatives in distance do not matter. So it's 4 and 6. So we have 4 squared plus 6 squared equals c squared. So 16 plus 36 equals c squared. Add both of those together, we get 52 equals c squared. Square root both sides. That's where I bring up my calculator. 52 square rooted gives us 7.21, so 7.2, and the 1 rounds it down to keep it the same.